Right. How was everyone's weekend? Good? Okay. So this week, the material is this model-based approach, Dyna. You should be reading up on it and do the exercises. But we have talked about it, or mostly. I mean, there are many variations of how you can do things. In my opinion, at this stage, they don't, like, these variations do not make much of a difference. I mean, there is not much advantage to be gained compared to just building a model and use dynamic programming to solve that model. You can save a little bit of computation by, once you're collecting more information from the word, you update the model a little bit. You don't have to solve it from scratch. You can have a warm start. But if you just keep running policy iteration, then, a few updates, it would fix itself. Later on, it will be more important if it comes to large state spaces and using various techniques to generalize across states that you haven't seen of how you're doing these things. And from that perspective, what the book is presenting, that's more interesting. But we will talk about that, I think, at the time when we will talk about this functional approximation business, as they call it. So I said that rather than going through that, we should be doing some worksheets. It's been a long time. And the worksheets have been updated. And we have lots of problems to talk about. So we can start with the worksheet. I don't know, maybe I wait a little bit with that. I don't know, how many of you have already read the respective chapter of the book about this Dyna algorithm? Not yet. Okay, so I wait a little bit, and then maybe on Wednesday and Friday, we're going to look at this worksheet, but let's look at the previous worksheet now. I assume that everyone is already familiar with temporal different methods for control. It's been the last week. We talked about them, and you had quite a bit of time. So let's look at the worksheet of that. All right. So, oh, the window is not even maximized. Good. And maybe if I download it, who knows whether I can open it and then it will be better or not. No, it just goes back. System viewer. Hey, come on. Oh, it disappeared. All right. It's just a little bit slow. Okay, Adobe Acrobat, maybe it's going to be good. It starts. Did it actually start? Box Manager, yes. It hasn't started. All right, maybe while it starts, it's almost as good as would be. So worksheet number 7, TD methods for control. We have one MDP, and we need to answer a bunch of questions about it. Then How many? We have 8 questions. Okay. We have 40 minutes, 5 minutes per question. That's ambitious. We won't be done. So the very first question is a lot of text, but it's basically just have this MDP and then figure out things about it. And figure out about like what happens to Q-learning. Have anyone? Yeah, no one looked at this worksheet. It just came out, of course. So the first time you see it. Okay, so this is just about some basic questions, and then what happens with Q-learning if you feed it with some data and SARSA. So just practicing those things. And then this is about SARSA. And it's more like a knowledge question. This is also a knowledge question, Q-learning. Oh, this is going to be quick. Yeah, I'm inclined to start with that. All right, let's start with this. This is a warm-up question. Why is Q-learning considered an off-policy control method? I hate these questions, by the way. But it's important. It's terminology. It's what people would say. And like, it's important to understand. What do they mean by off-policy control if they say that Q-learning is an off-policy control method? So we need to know what is off-policy and what is control. So what is off-policy? It doesn't follow the greedy policy. In Q-learning, you don't need to follow the greedy policy. The behavior policy doesn't need to be the greedy policy, and we're still learning about. Why is it off policy? You're giving me half the answer. I think you know, but yeah. When do people call something off policy? Like, we have seen this word before. Yeah, like an algorithm is an off-policy method, they would say. Like, for example, for value prediction, TD learning, you can also have an off-policy method. You mentioned the behavior policy, something of that kind. I think you're on the right track when you're thinking about behavior policy and some other policy, target or something. Yeah. And so when is it off policy, when is it on policy? So when they are not equal, then it's off policy. When they are equal, then it's on policy. And what does the behavior policy do? It's used. It is used for something, yeah. And what's the meaning of the target policy? Well, greedy or not, it could be some other policy as well. I think in general, the meaning is just that that's your target. You want to learn about that policy, like its value. You want to learn about its value. Good. Thank you. So off policy is when you have some data generating mechanism, it maybe follows a policy, and that policy that is being followed is not the policy that you're learning about. So what policy are we learning about in Q-learning? Whose action value function are we learning? Which policy is that? Yes, exactly. We're learning about the optimal policy. And in Q-learning, we do have the option of not following the optimal, but actually not just the option, but it would be hard to follow the optimal policy when you don't know the optimal policy. So most of the time, you don't follow the optimal policy, yet you're learning about the optimal policy. And so that makes Q-learning an off-policy method. Okay. Control. What makes a learning method in the context of reinforcement learning control learning method? Control. Yeah. No. Yeah. Oh, yeah. What makes a learning method in reinforcement learning a control method? Which policy? Yeah, we're trying to learn what the optimal policy is. Then we're talking about the control method. And for Q-learning, is that true? Is it learning about the? Is it learning what the optimal policy might be? You're saying yes. Why?
Learning off of the optimal policy, but using different actions, but you're still learning off of that optimal policy.
Okay.
Yeah.
Generally, the control would mean that you're kind of learning what actions to take. It's like maybe you're learning at what state what action to take. Is Q-learning doing that? How?
It's like based on the action value first, and then is greedy by on that to get the
Right. So it's kind of like doing it in a very indirect fashion by learning action values that are in the limit, if everything goes right, are going to approximate the optimal action value function, in which case taking the greedy actions with respect to these learned values is going to be an optimal policy. So I would say, yes, it's a control method, or you can use it as a control method if you just add this greedification step. All right. Okay, one's done. This is also short. I like short. Suppose the action selection is greedy. Is Q-learning then exactly the same algorithm as SARSA? Oh, what is SARSA? Yeah. I feel that maybe the best would be to write an equation on the board. Are you willing to do that? Oh, that's fine. We'll fix it. Huh? What? Oh, no, no, no. Oh, you're doing that?
It both involves like this thing where you input that.
Okay, some target.
Before we had the next reward plus.
No. Yeah, it's good.
Something in there.
Wow. Write it.
The max of the next state. Their action, so you're maximizing it over the next action you can do.
So call it maybe not A prime or something.
Sure.
And the max is over A prime.
This Q-learning.
Oh, wait. There is a syntax error. I'm parsing this. Yeah, that's good. There is something missing here. After the max, you're maximizing a value. What value? Q value. Good. And then maybe put an A prime there. Good. You didn't get it wrong. This is Q-learning. And now with SARSA,
we're still changing what this two is.
Yeah.
And the alpha and this part's still the same. But I'm going to write the big formula here first, which is the expected value of the next. Well, this, and you find this probably using the policy or this is probability, right?
Yeah, fine.
And
Usually we write the state as second argument. It's like given where you are. Oh, that's a probability, I see. Where is the, okay, pi should take an argument a prime as well. Good? Yeah.
something might be.
Almost correct.
That's
Very
as far as I
close.
know, there's something-
No, I mean, like you got it wrong. It's just you're too close to the board. There is an S prime over there, right? Because you wrote an S prime. So that's the next state.
And this is still
And you just wanted to expand what the expectation was doing. And the expectation is just taking expectation over the actions at the next state with respect to the policy. And that's maybe an S prime as well, because the policy is going to be applied. No, that would be very confusing. Because we are trying to create a target here. And here we are doing the bootstrapping. This bootstrapping part is about the future values. It's not the current value. The future value is at the next state.
So under all policies for the next, okay.
Got it? Yeah, that's correct. I think.
Copy this over to make it clean.
Okay.
And you can keep talking.
No, that's all right. We're not in a rush. Cool. Okay. Very close.
Then you brackets around.
That's correct. Yeah, sure. Okay, that's very, very close. This is not actually SARSA. What does SARSA, very, very close, we'll get there. What does SARSA stand for? It's an abbreviation.
State action reward. Oh, sorry.
Yeah. State action, reward, next state, next action. Okay. Very convenient that if you put it together, it sounds like an English word. It's a very cool name. And you kind of have this here, except that you're going one step ahead. You're taking expectation with respect to this next action here. We're already doing that. So this algorithm is called expected SARSA, or expected SARSA. I think the book calls it expected SARSA. And the SARSA algorithm is lazier. So it does the same. Okay, gamma. And then here, no max, no nothing. It's Q, S prime, A prime, plus 1 minus alpha, and Q, S, A. All right, so see the difference? Here, this A prime is going to be sampled from some policy that you decide. And that policy is going to be used at time step S prime. It's like as you go, you're collecting the data. Maybe you're using epsilon greedy or whatnot. Based on the most recent information, you decide what policy to use in every time step. And in SARSA, we just use this collected data, which can be chunked into these quintuples. Because this is a full trajectory. State, action, reward, state, action, reward, state, action, reward, and so on and so forth. From that, you take a chunk like this, and you apply an update rule. This update rule over there. For every little chunk, that's going to be SARSA. Okay? And since it's on the board, and it's going to be the subject of some questions, this is expected SARSA. So instead of just using the action that was recorded in the data you would record the action probabilities for all the actions, and that's your little pie here. Okay, so then your data, so here for SARSA, the data would look like you have state and action and the reward and next state. So this is more like the math notation where we have indices for all of these things. And that's more like the computer science thing, because like, okay, like locally you can rename these variables. I just take these guys. And so these guys become these guys. Okay. They're mapped one-to-one. But you collected a trajectory like this, and then you, as soon as you get to this point that you got this guy, you can do a SARSA update. You have to wait until you get this action. Before that, you can't really update this. So you need a little buffer, like compared to TD learning. TD learning only cares about up to this point. And in SARSA, you care about the next action. OK, so if expected SARSA, you want to apply expected SARSA, then you also need to save the probabilities for all of these actions. So you would save, and these probabilities would be just saved for this next state. So as you go, for every state that you visit, you compute a policy. Maybe it's epsilon greedy. And then you record the corresponding probabilities. OK, so you create a little table of, OK, what's the probability of, I'm going to call it P. So here is the first time you're recording it. So you're going to record PT A, OK, for every action A. And here you're recording PT plus 1A for every action A. But of course, these recorded probabilities are going to correspond to what you would do in that state. So let's say you apply epsilon greedy. Then there is the greedy action. For the greedy action, the probability of the greedy action according to epsilon greedy is what? So there is the greedy action. What's the probability? Of the greedy action in epsilon greedy? Well, there's the coin flip. It has to come out right. So the probability of that is 1 minus epsilon. It's a large number, hopefully. Epsilon is small. And the greedy action can also come up because you just happen to choose it random. So the probability of a greedy action is going to be 1 minus epsilon plus epsilon over A. And the probability of a non-greedy action is going to be what? It's just epsilon over A, right? So then when you're saving a table like this, you would just see these numbers, like two different numbers. One is epsilon over A, and one is 1 minus epsilon plus epsilon over A. You save those numbers, record them, put in a buffer. So when it comes to apply the update rule, you can just take those numbers and use those numbers in the update. So you wrote pi, but this pi is kind of like, OK, a little bit indeterminate, but it's OK. Like this pi, we can bind it to these numbers. So this pi is actually these numbers that you're saving as you go. So that's how you implement it, right? OK, that's going a little bit further beyond this question, because this question was just about SARSA. But OK, very soon we will see questions about expected SARSA. Is this clear? Expected source is a little bit more complicated, right? Like source is really simple. You just save the data. As soon as you can process it, you apply the update rule. And the update rule happens to be actually simpler than Q-learning. There is no max. Questions? All right. OK, back to our question. I think we can keep this on the board. Suppose the action selection is greedy. Is Q-learning done exactly the same algorithm as SARSA? OK. So now we are in a position to answer this question. Just wants to know whether the update rules are going to do exactly the same thing if you apply SARSA, which is this, or Q-learning. And in SARSA, these recorded probabilities are not like, OK, it's epsilon greedy with epsilon equals to 0. All right? So let's think. Are they the same or not? OK, who says yes? 1, 2, 3, 4, 5, 6, 7, 8, 9. OK, who says no? 1. OK. You're on stage. You don't want to be. OK, it's fine. But you're right. And actually, who wrote? Oh, wow, OK. OK. So they're almost the same. There is a slight difference. So the slight difference is that in Q-learning, when you apply this update, you're here. You processed SAR S prime. You're here. You haven't decided about A prime. You apply an update. What is that? The maximizer action is based on the current Q values that are actual at time t. OK? What happens? OK. Let me just finish. What happens in SARSA? Well, as I explained, you go, you do the updates. When you come here, you have the update. You will have the update, but what are you recording here? OK, I think I was wrong. You haven't updated yet. OK, so it's complicated. I said that, oh, OK, like it's going to update, but no, it's not going to update. So the update only happens once you produce this. So when you're following the greedy, what QT value are you talking about? When you're generating this action, AT plus 1, what is this based on? It's based on the values that were produced at this time step, here, QT. OK? So then this produces this. But this was produced by whom? If this produces this, it's like one step later, there is this delay. Then this guy must have been produced based on QT minus 1. If QT and QT minus 1 are not the same, these might be different. And of course, we are updating QT. So OK, we're back to you. You're correct. This is what you were thinking about. Exactly, right? OK, good. Yes.
So isn't that like, if the policy that we're actually think about the rapid action
Mhm.
that we're actually not the optimal action value?
They're being updated.
Yeah, started learning about its current policy. I mean,
I wouldn't say, yeah, because SARSA eventually, if conditions are right, was, I mean, it had the potential to learn about the optimal action value function. I mean, like you can apply it with epsilon greedy, with epsilon goes to 0, and then it's going to learn the optimal action value functions. But both of them are changing the action value function. So here they are literally asking whether if you run these two algorithms on whatever MDP you consider, in every single time you will get the same answers. And the answer to that is no, because we could construct an example, but this is not happening. And the reason for that is because the Q values are changing underneath SARSA, and it's generating a different sequence of actions than Q learning would with greedy updates or greedy behavior policy. Yes.
Earlier, totally different matter. But that means like the randomness of picking a new. In Sarsa, when you choose your new action,
Yeah.
there is sample rather than the
It's random for sure. Yeah, it could be random. I mean, like
Does that happen?
it is greedy, so it's like given the Q values he recorded, it's deterministic, but the Q values recorded depend on past experience, which is random. So it's like, okay, it's random and not, but the same is true for kind of Q learning. So that at that stage there is not much of a difference, but it's like there is very sneaky way they're actually different. In order to see this difference, what would need to happen? You kind of would need to have a meaningful update so that these actions are different than those actions. I think what would need to happen is that you go back to the same state. So for example, if you're in a tree or kind of like you can never go back to the same state, I think that they would produce the same things. If you're not in such a situation, then you can have different outcomes. And these things are actually important because if you implement an algorithm, then sometimes you want to cross-check things and then double check whether you correctly implemented. And you would consider an edge case like this, and you expect, oh, they should be doing the same. Okay, if you don't run a lot of experiments, then maybe they will always come out the same. But okay, there are edge cases when they are not. Okay. Yeah.
I was just opening
The solution was incorrect. It's lost. So I'm updating these worksheets. And so you're welcome to look at the old worksheets. I might not agree with the answer. And sometimes I do change the questions too, to make them a little bit more precise. Yeah. So don't believe the old worksheet answers. You don't have to believe me either. Prove me wrong. I accept that. I'm wrong often. Yeah. I see. Yeah, yeah, like non-unique maximizers easily break all these claims. So I guess implicitly it was assumed in the question that if you have two actions which have the same action value, then you're breaking ties in some systematic way in both algorithms. Because otherwise, yeah, we would run. And actually, when you're implementing things, this may come up, although it has to be a very artificial example for the Q values while you're updating them to be exactly the same. In discrete settings, it may happen because you're just have few options. So then ties could happen. But if you have any real system, usually don't happen. Yes.
Oh, what do you mean by action? Like if you have, I know that's not like you learn this for
Mhm.
Are you supposed to, like, is it like you're making decisions with parser algorithm as you're going through the episode, or is it like you already have an episode that already shows all the actions based on its own, some other like action?
Wonderful question. It could mean both. It's somewhat a vague language. I think if you are reading the book very carefully, then the intention seems to be that when they are talking about the action selection is greedy, that means that you're running this online algorithm as it goes, and it keeps updating how it selects the actions, and it's going to be greedy. Especially since we are talking about control here, right? Where we also take into account how we are generating the data. But you're absolutely right. You could imagine a case where someone would say that, well, I have a greedy action selection, but greedy with respect to what, right? Like it's not really specified. It's meant implicitly that, okay, in the case of Q learning is the current Q values. In the case of SURSA, it's again the current Q values. Yeah. But you could have something like someone fixes some Q values, and then you generate the data in a greedy fashion with respect to those Q values, and then you process it either with SARSA or Q learning, you would get the exact same results. Okay. All right, so maybe I revised the question a little bit by explaining that action selection is greedy with respect to the most recent Q estimates. Yeah. That's right. Yeah. Well, eventually they are generating different data, so the values that you're going to get are different. And so here it asks whether they are the same algorithm. So what is an algorithm? It's like it goes in and, okay, maybe it interacts in this case with some environment, it produces something. When would I consider two algorithms to be the same? The code can look different. If they produce same results under identical inputs, then they are the same. Since we are in an MDP, it's kind of complex because it's like randomness and whatnot. But okay, like literally, what we mean is that, okay, with the same seeds, running with the same seeds, if they produce identical results, then they are the same, implementing the same abstract algorithm, right? But they're not. Okay. Yeah. Okay. So the second part we already answered. Are there any downsides to this choice? But the choice is this action selection is greedy. This is a freebie. It's not meant to be a deep question. Would you ever consider running these algorithms with greedy action selection to generate data? Yeah.
Your environment is like not very like in
Mm-hmm.
some other thing that's voicing feature and causing it to thinking
Okay. You're thinking about the Clifford. Uh-huh.
sorry, not
Clifford, yeah. Falling. Yeah. So we saw there a very surprising example of that. There are two algorithms, and one of them is trying to learn about the optimal policy, Both of them are using epsilon greedy with a fixed epsilon to generate behavior. And one of the algorithms, which is not learning about the optimal policy, not using Q-learning, but uses, I don't know, SARSA or expected SARSA, is definitely producing better values and definitely producing better behavior. So that seems to be a downside to if you are committed to explore, then learning about what is optimal to do and not taking into account that you already committed to explore by defining what's optimal is not optimal anymore because you're committed to explore. So greedy choices there. Is that a greedy choice there? There was epsilon greedy choice there. I'm thinking that this is more about this commitment thing. So here, I think there is something much simpler that the question is after. It's like, if you apply in a bandit, just choose actions greedily. Do you expect that this is going to be good? No. There is no exploration, right? We need exploration. So here the answer is just no. You need exploration. Oh, this is long. Question 5. Okay, variance calculations. There's so many of these problems about variance calculations. Maybe at one point we should do some of these. They're kind of the same. So today is the day for the short problems. Okay, what are the update equations for double? Oh, you can't. Oh, that's a good point. Yeah. So this is just a scary long problem, but it's just some calculations. It's actually not too scary, especially the first part is, you will see that I would answer that very, very quickly. Okay, shall we do the first part? Let's do the first part of this, but I'm not doing the challenge question. In this question, yeah, we have 6 minutes. Yeah, I can do this. We can do this together. In this question, we compare the variance of the target for SARSA and expected SARSA. Yay, we already know what expected SARSA is. Recall that the update for SARSA is this. Okay, so this is using our beautiful math notation. And for update for expected SARSA is this. So here, things are a little bit swept under the rug with this pi, but fine. Okay, so here it says pi is a fixed policy. All right. And you have, okay, just these histories. One ends with ST, the other ends with STAT. And show that, oh, if you take this up to ST plus 1, so you take this history, but you include ST plus 1, so you the full history up to state observed at time t plus 1, then this variance is going to be larger than this variance. Okay. So I'm telling you that there is a one-line answer to this that involves no calculation. Yes? With this conditional variance, it's like so the variance definition is that if you have a real valued random variable, then you can look at the mean. That's called the first moment. The second moment would be, the square of the value and the expected value of that. But here, the variance is trying to define how much deviation you expect to have from the mean. So you take the random variable You subtract from it its expected value, you square the whole thing, you take the expectation again. That's variance. And the condition of variance is the same, except that there are two expectations in this formula. Expected value inside that you were centering on, expected value of the deviations from the mean, that's the outside expectation. In both expectations, you take conditional expectation. That's it. And but intuitively, it's just like the dispersion of the values. Yes? Correct. And why is that? Why is that enough that the right-hand side is 0?
Variance is like the measure of that's what the value, or yeah, the value of the expectation is like the requirements.
Yeah. Okay.
So yeah, if you just take the, I don't know, if you just calculate it, it's gonna be 0.
It's gonna be, yeah, you're absolutely correct. We'll talk about why it's 0. I just want to say a few words about like why is it sufficient. So, sorry, what's your name? Mo? All right. So Mo says that it's enough to show that this is 0. Why is that enough? Because we know that the variance is definitely non-negative because it's the expected value of non-negative values. So how would the expected value of non-negative values, why is it non-negative, the expectation of what you take? Because we are squaring things, so those are non-negative values. So the variance surely is non-negative. It's above 0. It's at least 0. So if we show that this is 0, we are done. This inequality will hold. And then the question here, what is that we are taking the variance with respect to? Whose variance are we talking? What's random here? Well, we are conditioning the full history, including the last state, the skew values. There is nothing random. This is deterministic given the history. It's a fixed value. The variance of a fixed value is 0. Okay. So that's how much we could fit in for today. This part would be a little bit more calculations for sure. And next time we continue, I'm not sure about this worksheet. Maybe we start the other worksheet. Some mix of the two. All right. Thank you.